This program will deal with musical perception, the evolution of a musical instrument, and the making of a string instrument. Do you know how our brain goes about remembering a melody? As the brain tends to choose generalization over precision, it remembers melodies not as specific sounds or notes, but as a pattern of rising and falling sounds. Musical perception is a complex mechanism. Let's see how it works. Music has the power to make an adult cry or to lull an infant to sleep. That ability to stir the soul seems a mystery. Yet it is based on the physics of sound and on the inner workings of the auditory system that picks up the sound and the brain that analyzes it. Musical sounds are cyclical vibrations of air. A sound's pitch is determined by the number of vibrations per second. The greater the number, the higher the sound's pitch. Also, the swing of the vibrations determines the intensity of musical sound. The greater it is, the louder the sound. Lastly, an instrument sound has its own distinctive color, called tone. Indeed, a note's fundamental sound is accompanied by a whole series of secondary, higher-pitched sounds called harmonics. An instrument's sound or tone depends on the amount of these harmonics, on their intensity and evolution in time. When several instruments are played together, as in an orchestra, the ear receives a multitude of different vibrations. And yet the brain manages to sort them out. It is able to distinguish each instrument and to reconstruct the melody, weaving together the myriad sounds generated. It does this by responding to the pitch of the melody. Indeed, the eardrum reacts differently to the various frequencies it perceives. It vibrates slowly when the notes are low and quickly when they are high. These vibrations are then relayed through the auditory ossicles to a spiral organ, the cochlea. The cells located at the base of the cochlea detect high notes, and those at the top, low ones. This is what enables the brain to distinguish them from each other. So when two instruments play together, one in high and the other in low, the listener can perceive them separately. The brain takes another cue to distinguish the sources of sounds, namely the interval between the striking up of the various instruments. Besides the fact that every instrument has its own striking up quality, an instrumentalist can set himself apart from the ensemble by voluntarily delaying his entrance. This enables him to highlight the piece of music he is interpreting. However, for the listener's brain to be able to clearly distinguish the soloist from the other musicians, his delay must exceed 30 thousandths of a second. Subtle frequency modulations, like those of a vibrato, will also allow an instrument or a singer to detach himself from the rest of the ensemble. However, when the brain recognizes none of these clues, it combines the various sources of sound into a single sound. The magic musical sound works on us is largely a result of the way the sounds are arranged. Music of the Western world, among others, is determined by a complex system of relationships between musical notes. This system applies equally to popular music and classical music. Any person who has been sufficiently exposed to that musical system will find certain chords or progressions more harmonious than others. This affinity between notes is known as consonance and is explained mathematically. In Western music, the most harmonious chords are composed of simple numerical relationships. The octave, for example, is determined by a 2-to-1 ratio, which means that the frequency of the highest note is twice as high as the lowest note. This simple mathematical relationship gives an impression of perfect harmony. The fifth, associated to a 3-to-2 ratio, and the fourth, to a 4-to-3 ratio, are also perceived as harmonious. On the other hand, chords associated to more complex relationships give an impression of dissonance. When these chords are played, we hear rapid flicker noises. These flicker noises excite our auditory system intermittently, creating an unpleasant sensation. In spite of this, dissonances have long been used in musical discourse. They help retain the listener's attention by alternately producing states of tension and relaxation. However, a listener's sense of musical aesthetics depends largely on his or her general culture. We all begin to acquire the rules of the musical language of our culture early in our fetal lives. Regular exposure to music constructed according to those rules is sufficient for our brains to learn them. One hypothesis holds that, thus educated, a listener expects certain musical patterns when he hears a musical piece. If he recognizes familiar patterns, the music will seem harmonious to him. Conversely, the absence of such patterns will make the music confusing to him. That's why some exotic or contemporary pieces do not always seem melodious to the Western ear. The human brain is a masterful musical maestro. The way it masters the complex rules of music is simply amazing. Since science began to unravel the workings of the brain, the knowledge of our perception of music has been rapidly evolving. Musical instruments have also evolved. Take the flute, for example. Musical form has constantly evolved over the course of history. To meet the new demands of composers, musical instruments have also had to change and be refined. The flute, for instance, has undergone a veritable metamorphosis over the years. Still, its fundamental principle remains unchanged. In a recorder, for example, the lips of the flautist produce a thin airstream that strikes against the instrument's mouthpiece. The airstream begins to vibrate and relays its energy to the air column in the flute's conical tube. This produces sound waves, which correspond to zones of air compression and dilation. The waves ripple down the tube and are reflected at its end, much as those that run through a spring. What determines the flute's pitch is the length of the air column in its tube. The longer the column, the longer the waves will be, and the lower the resulting sound. Conversely, the shorter the air column, the shorter the waves, and the higher the sound. To lengthen or shorten the air column, the musician simply stops or unstops the holes. Indeed, the sound waves only travel effectively between the mouthpiece and the flute's first open hole. This phenomenon enables flautists to obtain waves of different lengths and hence sounds of different pitches. The ancestor of the flute was a whistle carved in bone. Other naturally hollow materials, such as reed and cane stalks, were also used. These primitive flutes had a drawback, however. Their bore, that is the interior measurement of the tube, was predetermined, as it were, by the characteristics of the material. So it was impossible to make two identical flutes. In the Middle Ages, to circumvent this constraint, the makers carved their flutes from the wood of fruit trees using wood-turning lathes. From then on, bores could be made to specification. This made it possible to modify an instrument's register while maintaining reasonable spacing between the holes. During the Renaissance, the transverse flute consisted of a long cylindrical bore and 6 holes that produced a range of 2.5 octaves. However, it took a deft fingering technique to produce the full range of tones. In addition, the precision of certain notes left something to be desired, and the skilled flautist had to correct them by modifying the position of his lips. Around 1700, it was discovered that a conical bore produced better results. To carve this new shape with greater ease and accuracy, the body of the flute was divided into sections. Thus transformed, the flute yielded truer notes and a richer sound. The holes were arranged for easier finger play, which allowed in turn for greater virtuosity. Then in the 19th century, several new holes were added, bringing their total number to 12 or 14. Each note was then produced by its own hole and could be played with equal intensity. A key system was also introduced to make it easier to stop the numerous holes. Wood was traded in for metals like silver, which produce a more sparkling tone. This improved flute played with greater volume and could now compete with other instruments in the orchestra, such as the violin. The flute continues to evolve to this day. For example, a simple experimental device, activated by the thumb, enables the flautist to produce the quarter tones found in modern music. Thanks to this device, the musician can play several notes simultaneously. Today, the analysis and synthesis of sounds by computer are pushing the limits of the flute back even farther. The researchers first record the natural sound of a flute in an anechoic chamber. The walls in an anechoic chamber are completely covered in a sound-absorbing material that prevents reverberation or the reflection of sound waves. So it is possible to record the pure sound of the instrument. The recording is transmitted to a computer that calculates 300 times per second all the sound's parameters, its slight nuances in pitch and intensity, for example. The computer also measures the range of the various harmonics that make up the instrument's tone. All this information is then processed by a computer program that has the capacity to increase the instrument's range and possibilities. By increasing the speed of playing beyond that of an experienced musician, it is possible to create an ultra-virtuoso flute. The computer will also modify the tones of sounds by altering certain harmonics. It can draw sounds out and even completely take out the breathing noises that usually accompany them. The sound of the flute can also be hybridized to that of another instrument, such as a vibraphone, to create a vibraflute, combining the vibe's percussive striking up to the airy timbre of the flute. Scientists and musicians are working together to improve musical instruments. Their joint efforts help broaden the range of possibilities of musical composition. Research on children's musical aptitudes suggests that we begin to organize musical patterns at a very early age. No wonder instrument makers armed with only their experience and intuition were able to design string instruments that were virtually perfect. Violin making, or the art of making stringed instruments, is centuries old and to this day is practiced with the utmost fidelity. A violin is an arrangement of 4 strings mounted on a sound box. The latter is composed of 2 tables, the top, called sound board, and a back. Ribs form the intermediary part uniting the 2 tables. a piece of finely chiseled wood called a bridge ensures the contact between the strings and the soundboard. When the violin is played, the vibration of the strings generated by the bow is transmitted through the bridge to the soundboard as well as to the volume of air in the sound box. The violin's sound comes from the vibrations of the soundboard that agitates the ambient air, creating powerful sound waves. The vibration of the air in the sound box is, for its part, transmitted to the ambient air through two F-shaped orifices called sound holes. These other sound waves help round out the violin's sonority. Violin makers take great care in selecting the materials they use. Various criteria guide them in their selection. Spruce, a conifer, is used for the soundboard. The piece they choose must be absolutely flawless. Also, the growth rings of the wood have to be almost perfectly regular and evenly spaced, 1 or 2 millimeters apart. Such regularity is generally found in trees that have grown at altitudes of between 1,200 and 1,500 meters in stable climatic conditions. For the back of the sound box, the violin maker uses wavy grain maple wood, which presents alternately light and dark stria. This characteristic is sought after solely for its aesthetic qualities. Before being used, the pieces of wood undergo drying periods of between 10 and 20 years. The violin maker begins by tracing from a model the shape of the soundboard and the back. He cuts them out and shapes their curves with a jigsaw. Then, under the soundboard, he glues a long strip of wood called the bass bar. The bass bar, placed parallel to the strings, supports the pressure of the low strings. The high strings are pressed in playing on a small wooden cylinder called a sound post. The sound post is detachable, and changing its position will influence the tone of the instrument. Once he has completed the body of the violin maker makes the neck. He covers it in ebony, a very hard wood that will withstand the hammering of the player's fingers. To assemble the 70 parts that make up a violin, the violin maker uses a natural glue of crushed and boiled fish bones or rabbit skin. The advantage of this natural glue is that when repairs are needed, it is easily dissolved. The final step consists of varnishing the instrument. Besides giving the violin its characteristic color, varnish protects it from humidity and dust. A varnish mixture of solvent, various resins from oriental trees, and other substances is applied in a series of coats. All that now remains is to install the strings. Today's strings are made of a synthetic material, perlon, around which threads of metal of varying density are wrapped. The low strings are wrapped in silver, those of the middle range in aluminum, and the high strings in steel. The art of violin making developed empirically, that is, through intuition and experience. Researchers have attempted to find out if it can be founded on scientific principles. They conducted laboratory tests using ultrasound to measure the acoustic properties of the wood. First, they sent ultrasonic sounds through small cube or disc-shaped pieces of wood. They then measured the speed of propagation of the ultrasonic sounds, calculating the time they took to go through the small pieces of wood. In another test, using microscopes, they studied the wood's internal structure, that is, the shape and arrangement of the cells that compose it. Their experiments confirmed that the vibrations travel at greater speeds and their frequencies are higher when the growth rings are narrow. This is ideal for the violin with its high-pitched register. The testing also revealed that, owing to its simple and even structure, spruce facilitates the propagation of sound vibrations. On the other hand, the wavy grain maple used to make the back of the instrument presents a more complex structure, which helps muffle the sound. In the final analysis, the researchers came to the conclusion that the violin makers could not have made better choices. Although they may have lacked advanced scientific techniques, the violin makers of old managed to produce, simply through intuition and experience, instruments whose quality has yet to be equaled. Music reflects the workings of the mind. The ebb and flow of music has also been discovered to exist in nature, from the flow of the Nile, to the beating of the human heart, to the wobbling of the Earth's axis. Could it be that music reflects the harmony of the cosmos as well?